Hi guys, welcome to lecture 3. So today we're going to kind of do a little bit of cleanup here and with machine learning, just so we kind of get everything set. So we'll talk a little bit more some machine learning concepts, and then we're going to look at it from kind of more of a probabilistic orientation, which I think is helpful. And then we're going to do the introduction to reinforcement learning. Okay, so this is from Tom Mitchell. It's a really kind of compact way to kind of put things in an organized way. So a computer program is said to learn from experience E with respect to some class of tasks T and performance measure P. Now, if the performance measure at the task in T as measured by P, if that improves with experience, then we can say that the machine is learning. Okay, so it's a really kind of nice way to kind of cut it up into factor the whole question, kind of look at it in separate little pieces here. So the task, let's talk about the task T here. So this is how the machine should process an example, which is kind of a collection of features. So most generally, most general way of looking at this is we look at an example as a vector of engineered features over a task domain. So in this case here, it's a set of real values. And then some of the kind of tasks that we would have would be a task related to, for instance, classification. So we might have a task where we're looking at a whole set of features, and we're deciding which class that example belongs in. So like image recognition would be a kind of a simple example of this. Then there's regression. Regression is we're not mapping it to just a single kind of one of k classes. We're mapping it to a real value. So this might be kind of credit worthiness or something in a financial domain. Another way of looking at it, or another type of task, would be something where we're actually getting a probability density estimation. So what we're doing is we're observing a whole set of examples. And then from that, we're building some type of probability or some distribution over those. Just so we're kind of this typically relates to the unsupervised case, where we're just observing and then we're learning something from the observations. We're learning a probability model. Now, as computer scientists, we probably tend to prefer to think in terms of, instead of real values, a sigma here, which are basically finite sets. Okay, so you can everywhere you see an R here, you can put a sigma. And this basically means that we're actually looking at probability mass, not probability density. All right, so we're building the probability mass estimation. All right, so kind of more concretely, here are some types of tasks that were discussed in Goodfellow, which is the big deep learning textbook. Just prior to Transformers, so it was 2016. So it's interesting here. I mean, you can kind of look and see. So there's just the ones I've already mentioned, the issue of classification, regression, and probability estimation, probability distribution. But there's other ones just like so there's special cases of classification, say with missing inputs. That brings up special things. Transcription, so you have a scene, machine scene, and then you want to generate text that kind of is like the caption of that image. Machine translation, of course. I mean, we have French to English, for example. So this is what the Attention is All You Need paper was looking at. They were looking at this task. Structured output, that kind of has now actually got a new kind of terminology. Anomaly detection, synthesis and sampling. This is kind of, if you read this in Goodfellow, it's almost like anticipating GPT before its time. Denoising, etc. All right. So some more specific natural language processing tasks that we're going to be looking at in this course are tasks like classification. Okay, so this is like a sentiment analysis type task, where we give it a sentence and then it's supposed to determine whether it's a wholesome sentence or a dirty sentence. So eating milk and cookies in the sunset is wholesome, whereas John drinking a fifth of vodka and then barfing in the taxi cab would be classified as dirty. Okay. Entailment is like this textual entailment. There's a lot of work that surrounded textual entailment. So that is like, is it true that when I say that John sped off in his powerboat, does that entail? Does that mean that he left the area? Okay, so yes, it does. Okay, so in this kind of textual entailment type task, if you can, so what you're presented with is it either does or it doesn't. So John sped off in his powerboat. Does that entail that John likes cookies? No, it doesn't. It doesn't entail that. So that would be an example of false. It does not entail. The first sentence does not entail the second one. Similarity is another thing where if I say John likes boats is 98% similar to John loves boats, but only 53% similar to Bill likes Samantha. So these determinations of how close sentences are semantically, that winds up being one of these tasks as well. Now, the question you might say is like, well, who determines what's close together semantically? And the point then is that undergraduates get being paid to be part of a study do. So what they do is they develop a gold corpus of humans making these judgments. Maybe do some normalization. They have to kind of set it up in the right way so that they don't get wildly different results. But for any particular person, it should be coherent. So in other words, you should be able to kind of normalize things so that you can kind of get a useful data set. And that's in fact what there is. There exists a gold standard of these similarities. So then basically the question is how close can we get a machine to the gold standard. Finally, we have a kind of a question answering, but a simple version of question answering. That is, what are the multiple choice. So what is largest areas, U.S. state? That would be Alaska, right? Okay, so these are some more specific tasks. So this is the T in the machine learning, that we experience. Now let's go to the E, the experience itself. So how does a machine learning algorithm experience its training set? Okay, so now we're going to talk a little bit about the three main paradigms of machine learning currently, and that is the supervised. So the supervised machine learning, where what we're basically experiencing then is basically we have a label value or vector, which is y, which is associated with the training example x. So x should map into y. That's the experience of the data sample as it comes, as the machine's doing its learning. It sees a whole bunch of those in its training set. Okay. Now with unsupervised, what it's actually doing is it's what it's trying to build up here is it's basically given, what it's given is just a whole bunch of samples over some type of probability, over some distribution. So for instance, in the example of, for instance, if we have like Shakespeare's Macbeth, we have a whole bunch of 10-word sequences that, we can window across that whole data set. And then each of those can be an experience. Each of those, okay, here's another sentence in Macbeth. Here's another sentence. And then from that, what you can do is you can build up a probability distribution of what's the likelihood of sentences in Macbeth. So you build a giant probability distribution. Now, reinforcement learning, which we're going to talk about at the end of the lecture today, what we're given is a reward or punishment from the environment after actions are taken. So it's a little bit different than, it kind of stands a little bit separate from, and a little bit harder to kind of present just as a data set, because what you have to present instead is you have to present some environment where the agent can experience the environment, perform actions in the environment, and get reward or punishment signals from the environment. So an example of this might be the following. If you think about, let's think about this for 1 second. Let's think about Pac-Man. Can we supply, remember the little yellow guy who eats up everything? The video game. Right. So Pac-Man, what's the environment? It's like the set of pixels. So you see kind of the screen. There's your environment. And then what are the actions? The actions are you can just move the toggle, or you can move the joystick in 4 different directions, essentially. So you move it around through time. And then what is the reward and punishment? Well, the reward is just watching the score. Watching what the score is. So the more you're eating up, the better the score, the better you're doing. And then the punishment, of course, a major punishment is if you get eaten by a ghost. That would be a major punishment. So it's not really a data set that's been kind of spelled out, but it's like a little environment in which you can experience the data or experience the system and then learn from that. And just to let you know that the Pac-Man and the Atari games were solved. So just going from the very, they can play a really good video game. I think superhuman capability video game. In other words, they're better than the. I'm not sure they're better than all humans, but I think they are in the Atari. I have to kind of check on that. But that's an example. So this is how things are experienced. Supervised, the experience is just a whole bunch of input, and then what's the class? What's the correct answer? Samples. Unsupervised is just raw samples from a distribution, just kind of like here they are. Nothing that says, no labels, just kind of observing. And then reinforcement learning is some type of little or some type of environment that you can kind of hook up. Okay. So now that we have that, then we want to talk about what's the performance measure. So if we present these kind of experiences, so the class is the first thing for the problem, the first thing that gets kind of decided. This is the class of problem that we're looking at. Then we kind of have a training set, right, of experiences, and the training set then induces a system then that actually can perform it. And then the question is that, well, is it better than just like throwing darts at the board? Is it better than random? Is it getting better through time, et cetera, et cetera? So the question is that how do we evaluate how well it's learning? So for classification, it would basically be that we would hold out a test set. We'd have a test set that we would hold out. So we have, first of all, we just have the whole corpus of and then we hold out a test set, and then we train, and then we basically come in and we look at the, once we're done training, then we look at how does it do on the test set? And then the question would be like, for classification, how accurate is it? What percentage of the items or the examples in the test set does it get correct? That's kind of a simple way. For numerical regression, that if it's supposed to be guessing like a numerical measure, then we could use mean square error. Okay, but we're not going to talk about regression in this course, but there it is. Now, this is something that I think that maybe we're going to get some intuition about when we talk about probabilities a little bit later in this lecture. But there is this notion of, for a probability distribution, how do I know I have a representation of what's likely to happen? I've induced a probability distribution of this class, okay, of this tasks, this task class. I have a probability distribution. Now, how can I evaluate if I have a good one or a better one than I had before, or somebody else's distribution? How do I evaluate what's better? And the answer here is basically what you do is you take a fresh example, and then you basically say, okay, what's the probability that I think, whatever it is that's generating examples, whatever, I basically take an example and I look at it and go, what's the probability that I thought that would happen, or what's my surprise essentially, or what's my, I look at some kind of really normal example and I say, yeah, it's a probability of 0.8 or something. It's very likely that's what would happen. Well, what happens is I start just taking in examples from the distribution. I just kind of judge them. And then what I basically do is I'll wind up taking a negative log probability of them. And I'll show later on the distribution or the shape of that particular curve. But if something's 1, if it's completely expected, then that will basically be zero. The value will be 0 loss. Okay, so we want to minimize this in this case here. We want to minimize this average negative log probability. But as we'll see, it's always going to ultimately be positive. The average will ultimately be positive for anything that has any kind of distribution. But we'll see an example, a really concrete example here that I think will give you some intuition about why this works. Right. Okay. So we'll come to that. We'll come to this issue because it's kind of a little bit confusing to say average negative log probability. That could be a little confusing, but we're going to get to the bottom of that. I promise. So then for the reinforcement learning thing will just basically be something like, okay, I have an agent that I've learned, and then basically what is the I can just basically send it over a whole bunch of trajectories. Like, okay, here, let it loose in the environment, and see what is the average. What is the kind of the expected returns. What value am I sucking out of the system? What on each of those trajectories? And if I have one agent that I've taught through reinforcement learning that gets after I've run a whole bunch of trajectories and it's getting a really good value for its return, it's got a lot of rewards from the environment, and then I compare that to something that's kind of not doing so well, then this one is evaluating better. It's got a better, it's performing better. Okay, so right. So now, in any system that you build or you have machine learning for, what you have is you have hyperparameters, which are, let's consider the hyperparameters widely. So that might be like, what's the architecture of the network? What's the like how many hidden layers are there with this particular neural network? That kind of question. And as you kind of work on the problem, you might actually be implicitly changing these. So this can kind of almost be a leak. If not controlled for, but essentially you do have these kind of hyperparameters that you're kind of working with, and you're kind of you have a data set, right? You have a set that's given, that you can split into 3 distinct pieces, and I'll talk about those pieces in a second. So in a lot of times, like when people are doing this in academia, they're actually given the training set or the development set. And then when they're going to form a leaderboard, that's when they give you the test set so that they can evaluate it. So there's kind of, it's kind of a little bit removed from, so they can get an honest evaluation. So the point though is that the issue about the hyperparameters is that you might be going through this process of going through and evaluating kind of how well did it do now, and then it's like, I didn't do that well, changing something in terms of the structure of the network or something else. And so, now it's done better. Now it's done better. So that's actually you doing the learning, not it doing the learning. But at one point you arrive at some kind of architecture, some type of setting of the hyperparameters that do well. And then we can, of course, track learning. And we track the learning in the following way. We basically have a training set and we have a test set. So we have the training set. We're going to basically, we're going to do our training. Now, there's something called k-fold cross-validation. So with a k equals 5, what that means, it means that what we do is when we take our training set, we take out 20% of it, we set that to the side. So we divide it by 1/5. So we do that for the first sample, the first 20% of the data set, maybe under a shuffle or something. First 20%, and then we train on the 80%. And then what we do is then we just do a kind of a mock test, if you will, on that held out 20%. And what that helps us do is it helps us avoid what's called overfitting or generalization error. So we'll see on the next slide kind of how that works. But with k-fold cross validation, you do that for all 5. So you take your training set, maybe you shuffle it, then you take the first 20%, hold those out as your validation set, train over the rest. And then go and then take out the next chunk of 20 to 40% for what you hold out as the validation set, and continue to do that. Now, if what's happening is the validation set, you see a significant generalization error in the validation set, then you might change some aspect of the algorithm so that what you would want to see is you would want to see that it doesn't have this generalization error. So let's take a look at this. So this is the kind of the point here. So we have underfitting and we have overfitting, and then we have something that's kind of in the right, about right. Okay. So a lot of times when it comes to this, if you hold out your validation set, and then you're doing your training, you're searching for your weights, you're getting better and better. And then at one point it starts drifting. You start seeing error when you go over the validation set. Then you stop. You stop your training at that point, because anything beyond that would be overfitting. You would overfit your model. So what we see here, though, of course, is we have training error. So the issue, of course, is that if you really overfit it, then the training error, like whatever you're training on, you get better and better at. But that's part of the overfitting problem. So the validation set is kind of what this rests on. Everything, of course, rests on the nature of the training sets and the test set as well. And that's basically this assumption of independent and identically distributed, this IID assumption. So, right. I mean, so the idea is that whatever our training data is, that's drawn from the same distribution, from the same process that our test data is drawn from, and it's randomized. Okay. Right. So we want to avoid this generalization gap. Now, with a lot of problems with a lot of problems, what we get actually is a capacity a capacity issue. So if you're going to be basically, so if you pick a very, very simple kind of set of like, if you're doing some kind of fit of some very simple basis functions, there's only so much that it can capture. So the classic example of this is if you're basically you have some arbitrary function, signature, and you're trying to capture that with things out to a cubic, right? Well, you're not going to be able to kind of really fully fit the problem if you're, the real classic example is you're trying to fit it with linear. You have a nonlinear relationship and you're trying to fit it with a linear model. Then it's like, well, it doesn't really have the capacity to kind of express really the kind of you can't go to an arbitrary capacity in it to express an arbitrary function because it's based on like linear model or quadratic model or a cubic model. So those are the basis functions it can use. So it can only draw things. It can't perfectly fit things that are more complicated that would require more shape to them than that kind of a curve. Okay, so that's kind of an issue. However, in the case of neural networks, we have the following. That is that this universal approximation theorem. So again, most deep learning is using SGD, stochastic gradient descent, to affect the weights of a neural network, theta, to minimize some loss function. Okay, now a fundamental result, and that should be moved up here, is that any continuous function over R to over n-dimensional real space to m-dimensional real space can be approximated to an arbitrary precision by a single hidden layer with a sigmoid activation function and linear output layer. Okay, so the way this works, so it's easier to kind of see this. It's easier to see this when we're just mapping from a simple function where we're going from R to R. Okay, so just draw any random function you want. Just so any function that's doing any crazy stuff that's continuous, that's just kind of going. Okay, there we are. We have that. That function. It's important that it's continuous, but still, I mean, even if it's not continuous, it's like you can maybe like play some games to kind of make it so. So practically everything you can. It's very, very powerful, very high capacity here. Anyways, let's just kind of get some intuition about how this works. So if I have some arbitrary shape function and I have a very, very, very wide hidden layer, then essentially what's happening then is that each of those neurons in that hidden layer are focusing down to one. They're all zeros if they're outside of a certain x below a certain value and some range. There's some small little range, and if x, that is the input value, is below some value or above some value outside of that range, it just becomes zero. All right, that's what that neuron does. That one neuron in this giant hidden layer does that. Otherwise, based on what the value of x is it builds a little kind of bump. It builds a little kind of it builds a little tower there. So it's got this little tower there in there. And you can compose all these towers together to recreate any arbitrary function within a certain, precision. Okay. So it might be that we have the input, and then we have we have some complicated function. We have 10,000 neurons in the hidden layer, each looking at a small little part of the input domain, the X domain. And then when they get triggered, they contribute their tower, and that just gets plussed in. But all the other ones are contributing zero. They're contributing what their tower is. And by doing that, by composing all that together, you can do an arbitrary function. And this generalizes to n and m. So you can do it over arbitrary functional spaces. Okay, so right, so n could be 50, and it can be very multidimensional. Right. Okay, but what's the problem with that? Okay, it's good. It tells us that we have almost arbitrary capacity with neural networks. But what the problem, of course, is, there's two problems. One that I don't say here. One problem, of course, is that the architecture is kind of a little bit clunky to deal with. It is a hyperparameter to decide that architecture, essentially. But of course, the major problem is that hidden layer is way too wide. Now, an interesting theoretical result, and it comes actually from KTH, hurrah, hurrah, Hostad and Goldman did this in 91, is basically what they show is they show that depth matters, that depth helps, that you get much more expressivity in what functions you can represent. The deeper you go, the more you stack the layers. So basically, there exist some functions of depth in depth K networks. Okay, so if we have K depth with a linear number of neurons, so we have some kind of linear number of neurons in the system. That if we were to pull off the kth layer and say, oh no, let's represent the same function, but let's do it in k minus 1 layers. This leads to an exponential number of new neurons that need to be put into the network. Okay, so it just shows that you're getting that the deeper you go, if you try to step back, it may very well be that it leads to kind of this blow up, a la this universal approximation theorem type, where you just have this giant hidden layer. So it might be that it does well, but if you try to kind of make it shorter and then at one point it blows up on you. Okay. And I would actually it's interesting. I've kind of played around with myself. I haven't really gotten really strong at evidence yet, but I'm going to play with it a bit more at some time. Looking at this NIST example, or this MNIST example rather, in recitation 1, problem 4. So in other words, that would mean that, well, can we somehow get it so that if we have a deeper neural network, we can have overall fewer neurons or fewer weights in the neuron, and still do equivalent or to the performance that we were getting out of the one with a single hidden layer. It'd be kind of interesting to kind of play around with that and see how far we can get. Okay, so I think it's useful for us to adopt a bit of a probabilistic orientation, especially when we're going to be looking at the unsupervised case. So in this course, we really are only dealing with discrete random variables. So when we talk about joint distributions, probability distributions, we're talking about mass functions, probability mass functions, not density functions. So let's take a really simple example here to kind of clarify what we're talking about here. So consider the distribution Px, where x is a vector of n Boolean variables. This is a very simple case. So true falses. All right. So if we have 3 of them, that means that we're going to have, we can represent this distribution in 8 entries, right? Because we have 3 variables, all the true false combinations, that winds up being 8 entries. So this winds up being our mass function. Okay, so let's consider this. This is an example from Pearl's probabilistic reasoning book. But let's consider. Let's set the scene here where we have rain. Is it raining or not? True or false? Raining or not? Is the sprinkler on, or has the sprinkler been on? So it's can be a little removed in time here. So true, false. Sprinkler on, off. Rain on, off. Is the grass wet? Okay, so there's a relationship here. So let's just kind of well, we can maybe fill out this table. Okay, what is the probability of how much mass is there when we say that it's raining, the sprinkler's on, and there's wet grass? Okay, so that is, let's say that winds up being 0.05. So 5% of the time, all those 3 are turned on in this world that we're going to observe. Okay, so what's the most common thing? The most common thing is that the rain, it's not raining. There's been no the sprinkler's not been on. A sprinkler, by the way, just to Posvenska, that's the water, watering the grass, the thing that kind of moves and waters the grass. And then, so most of the time, the vast majority of the time, 83% of the time, in fact, that the rain, it's not raining or hasn't rained, no sprinkler, and also no wet grass. All right. But here, look at this case right here, where it rained, sprinkler, but the grass is not wet. That's kind of strange, but everything is possible, right? So for instance, here we have an example of, well, it didn't rain, there was no sprinkler on, but the grass is wet. That's 1% of the time. It's kind of a strange thing. But then we remember that Billy, the kid next door, was peeing on the lawn. So he peed on the lawn. That's why it's wet. Okay, that's kind of a simple kind of exception that could have could describe this little bit of mass here, is Billy peeing on it. This might be like, all right, what if we have the sprinkler was on, but the grass is not wet. Maybe the reason that happens is because the sprinkler was pointed in the wrong direction. Okay, so it could be something like that. So what's nice about probability is all the crazy examples. Like for instance, here it was raining, the sprinkler was on, but the grass was not wet. Well, the reason why that is because like inside of this 0.0001 are all the wacky potentials. Like one potential is that like some alien race kind of came down with their UFO and took out a big air dryer and blew it off, right? I mean, it's not very likely, but it's not, you can't just say, oh, it's completely impossible. It is possible in some universe, right? That's what caused the grass to not be wet. So this kind of probability theory is powerful in the sense that it kind of gets us beyond this quantification or this qualification problem of kind of classic logics. So it's kind of interesting. There's a lot of some interesting philosophical aspects to that. Anyways, this right here is a distribution over those worlds. Now, what I want to do now is first let's consider that distribution. Let's just get a couple things straight here, just to kind of some of the operations you do over that. The most important operation is what's called marginalization. So marginalization is basically how, if we look at this right here, if we look at this distribution here, and someone says, "Oh, that's fine." There's what's the probability that it's raining? What's the probability of rain? Well, you can't. Okay, well, here's where it's raining. It's raining here. It's raining here. It's raining here, and it's raining here. Okay, so there are 4 cases in which it's raining, right? So actually, if we sum these probabilities right here, that's the probability that it's raining. All right, that's the probability of rain. So right here, so it's 0.1011. So and then it's true and false, and it's 1 minus that for the probability it's not raining. Okay, so so how does that work? I mean, so that basically what it's doing is it's summing over all the entries. And so if you look at it formally, what you basically say here is what's the we have p x, and those are our 3 variables in this example here, and then we split it into y, which is what we're interested in. What's the probability of that being true? And that's a Boolean expression, by the way. So there could be this marginalization here generalizes to what's the probability of it raining and the grass is wet. Well, true and true, so it's 0.05 raining, and right here as well. So it's basically it's gonna be a 0.1 raining and it's wet. So you see those are the 2 cases. So what's happening here with marginalization is the Z set here. So these have to kind of together, they can't intersect, and they have to cover all the variables. But this basically, the Z set here is what you're going to marginalize over. That's what you're going to sum over here. And so this is kind of a formal way of saying it. Okay, so it's important that we have that. It's important that we can calculate marginalization. It's really simple. It should be really simple. Because now what we want to do is we want to talk about conditional probability. So an important point might be this, is that, well, what is the probability that it rained given that the grass is wet? All right, well, there's a definition here, right? And then what we get here is that's going to be the probability that it rained and wet is true given, divided by the probability that it's wet. This is just the definition of conditional probability. And by the way, that's a 0.625. So if I'm basically saying, gosh, the grass is wet, what's the probability that it just rained or that it was raining? Well, it's 0.625, right? So you can just kind of pluck that off, and you can compute it via marginalization. You can read it off the distribution. Okay, and then notice here also if I say, well, what's the probability that it rained given that the grass is wet and the sprinkler is on? Well, if you think about it from the point of view of common sense, that is like, this is kind of an explaining away type of phenomena. So the probability should actually go down that it rained, because now we have an alternate explanation for why the grass is wet. And that is that the sprinkler was on. And true enough, if you grind it over that distribution, you can wind up getting that the probability goes down to 0.5, right? Because the sprinkler was on. Now, what about this? What if we now definitely know that the sprinkler was off? Okay. What's the probability that it rained? Well, then actually just based on the mathematics here, it climbs up to 0.83, which is greater than what it is if you don't know that the sprinkler was false. Okay, so this is exhibiting common sense. This is really showing kind of commonsensical reasoning and adjustment based on what we know. What's the given can affect what the probability is. So it's kind of it's a pretty powerful aspect of probability theory. All right, so now what I want to show is how we're going to score alternative probability models. So we're going to go through a process by which we're just going to observe all these independent events of it raining, of different things happening. And we're basically going to have, Alice. So in this case, we have Alice, Bob, and Charlie. Alice has a probability distribution that is exactly equivalent to this distribution here. Okay. Now this is just what's in Alice's head. Okay, she judges this as the distribution, and we don't know what the true distribution is really. We'll talk about that in a little bit here. We don't know what the true distribution is, but Alice is guessing that was the distribution. Now, what do we have? Now we have Bob, and Bob's just a little baby. So Bob makes what's called a maximum entropy assumption. So Bob's model of the distribution is that everything's equally likely. Oh, all the different combinations, they're all basically 0.125 probability. Okay. So that's Bob. So we can already kind of feel that Alice should score better than Bob, right? But let's just look at Charlie, because Charlie's crazy. And Charlie basically is very set in his ways. And he says the probability that it's never going to rain, the sprinkler's never going to be on, and it's never going to be wet. He's adamant that that's a 1% probability. Nothing else is possible. Okay, so who scores best? Okay, so we're going to score this now by just basically taking a sequence of these observations, these trials, if you will, and assume this independence between the outcomes. So it's not like we're not watching over a span of time where maybe the atmosphere loads up with water molecules and it's more likely to rain. No, we're looking at it just kind of at the point of view of independence between the observations. So it's like flipping a coin. Okay, it's like kind of okay. So what happens? All right, so we go out and we observe. It's not raining. It's not, the sprinkler's not on, and not wet. Okay. So how do we score these? Well, we score these. Alice basically said, well, yeah, the probability in my probability model, I think that has a probability of 0.8379. Bob, the little baby, says, everything's equally okay. That's a 0.125. Doesn't have any opinion. Charlie says, yep, just like I said. Charlie's very, very. So Charlie basically scores a 1 because he said that was a 1 probability. Now, if we look right here, and we're going to just like evaluate them just after this one event, this one particular moment. And then we basically say, okay, what's the negative log of, okay, to this? So this right here is a plot of negative log. So notice here that at 0, it goes to positive infinity. Okay, so it just goes off the charts. Okay, so Bob is like right about here. Okay, sorry, 1.25. Bob, this is a natural log. So Bob is right here, roughly about there. Okay, so he's going to get a score, and we want to minimize the score. A high score is bad. He's going to get a score of like 2 something. What's Alice going to get? Oh, she's going to get a pretty small score here, right? Because she's going to wind up around there, I guess. But Charlie is going to get the score of 0, right? Charlie did really well, right? Charlie did well. All right. Now, in comes the next event. Same thing. No rain, no sprinkler, not wet. Bob's doing the same old thing. Alice, same thing. Charlie, the same thing. Charlie is very smug at this point. Okay, now in comes the next. And what we have here is we have rain and non-sprinkler and wet. Okay, so it's raining and it's wet in the grass. Okay, a 0.05% probability for Alice. Okay, so she gets a 0.05. So hers is 0.05, so it's like right about there. So she's going to get kind of a lot of penalty for that. Bob is still going at 0.125, but notice here Charlie now. Charlie basically lost his shit when he saw this because he said, this is impossible. He's just adamant. That can never happen. Charlie's very opinionated. So that's a 0. 0%. So basically what happens then to Charlie's score? What's 0 of minus natural log of x? Minus natural log of x at 0 is infinity. So Charlie just flunked. His score went off the charts. Okay, so this shows you it's best to never be so certain. Right? Okay, and this continues on here. Okay, so if we're going to do this as a product, if we're going to do this as like a product of the probabilities, so this kind of inverts it a little bit. So a product, the one way we might want to do this is we might want to say, oh, let's just take the product of all these things. And the one with the highest product is scoring the best. But those numbers are kind of ugly because they're kind of getting stripped off there. If we instead do the sum of the negative logs, well, Bob gets a 4.5, and Charlie gets infinity because the third trial just blew him. It's like that was it. It went off the charts. So what we do here, what we look at here is we look at the average of the minus. So this is when I was talking about average negative log as an evaluation. Look, Alice gets a 0.56. Yeah, that's hers. So she's scoring the best. Then Bob, and then Charlie. Charlie's doing the worst. Okay, so this is how that negative log probability works. This should give you some intuition about why this is an effective method to score distributions. Okay, so let's just look at this a little bit more right here. So let's say this is the P of nature. So this is the true distribution, right? This is what's really generating the truth. So Alice wasn't exact, but she was close, but not exact. This is the true distribution that's governing this example here. And then epsilon here is 1 in a million. So it's 1 over a million. Okay, so it's really, really small. Okay, but this is what it is. This is kind of how the world is really operating. Okay, so now we have this notion of what's called cross entropy. Okay, so it's kind of let me move myself there. So what cross entropy is you take two distributions. So we have the sampling distribution here, and then we have the inference distribution. So what you do then, and then you sum the. This is essentially doing the averaging, because what it's doing is it's basically something that's very frequent is going to be counted much more in terms of what its log is, and everything's being minused out front here. Okay, so if you play with this, you'll see that this is doing exactly what we were doing before. And if we look right here, we say like, okay, what if we have nature deciding the cases? Nature's kind of like throwing out the random trials, and nature is also what's judging them, or it's like, so it's the best possible distribution. Okay, even in that case, it's not going to be a cross entropy of 0. It's just not going to be. It's just doesn't work that way. The cross entropy then is 0.3760. Okay, that's it. Now look at Alice though. So if nature in all these cases, in these cases here, it's nature that's deciding the trials. Nature's kind of like throwing out the trials. And in this case here, Alice is going to be judged, and she's actually doing pretty well. She's getting close to kind of what's optimal, right? So she's minimizing. So, she's as maybe Alice is doing more training, and if we're kind of minimizing cross entropy, so we're trying to kind of we have a loss, the cross entropy loss, that she'll actually ultimately converge toward nature here. But in the current process, she's kind of headed in the right direction. Bob is, Charlie, hopeless. And this is kind of interesting here. Alice, these are just kind of interesting experiments. Alice kind of relative to Alice, Charlie relative to Charlie. Notice when if the sample is being generated by Charlie and Charlie is the one that's judging it, then we actually do get to a 0 cross entropy. But that's very particular. Bob, which is maximum entropy. Okay, so then the question is that what is this in base 2? So this kind of goes back to information theory. And the answer is 3 bits. You need 3 bits to decide under this. So it kind of relates back to like Shannon stuff. So you can kind of see some of that come out there. So I think this is a good example to kind of play around with, because it's very concrete, it's very simple, and maybe by playing with this, you'll kind of get some intuition around all this kind of stuff. Okay, so this is it more formally. So this is basically saying, okay, well, we got the probability of nature. This is what nature's kicking out. And then we have all these independent examples coming in. And the question is that what do we want? We want to basically we want to find a, okay, so in this case here, the reason why it's max is because we got rid of the minus. So these are all the negative territory when it comes to, we want to maximize the, okay, so we want to pick, if we can just pick the thetas that guide our model, we would like to have a theta that basically, if we took the products of all the probabilities in this kind of sampling thing, that it would be the highest, that it would be that it would be the highest product through. So we would want to maximize theta, whatever the parameters are of our model, so that we would get the highest kind of product of probabilities. And then this right here is just saying that, okay, this is like saying that we want the, okay, this is actually what's saying that exactly. So it's doing the product, but then what we can do is say, well, that's equivalent to basically taking, to doing this in kind of log space. So we're taking a log of it and we're doing the sum. Okay, so this is just kind of like showing kind of from a theoretical point of view, what we're looking for. We're looking for the parameters that guide our model that will then wind up maximizing this, or it would be minimizing it if we put a negative out front. Okay. And what's cool is that this also relates to kind of the supervised case where if we're given a distribution like this, then what we can do is we can do conditional probability statements that kind of recreate the supervised case. Right. Okay. So I hope that, study these slides and kind of try to get some kind of intuition about this, because I think it's worth it to kind of be able to see a little bit deeper into this. Right. Now, what we're going to do is we're going to switch over to reinforcement learning. We're going to talk about that now. Okay, guys, let's just cover at least some of the introduction to reinforcement learning, because we'll find it useful later when we look at reinforcement learning via human feedback and from reinforcement learning via verifiable rewards. So we want to build some background in this. So yeah, the reinforcement learning has roots in Markov decision processes and Bellman's dynamic programming. So it goes back a long way. So let's just kind of look at a simple example, a very common example of a cat. And in this case here, we have our long lost cat, Borchka. That was our cat. And basically we have a state space of 6 states. There's 6 different states here that Borchka can be in. State 1 is right here, and there's 0 reward. So if Borchka is in that state, there's no punishment, there's no reward coming from the environment. If Borchka makes it to this state here, state 6, then there's a bowl of milk, and that's a positive 1 reward. So that's good. If Borchka comes here to where there's snow, Borchka doesn't like having snow under her, toss her under her paws. So that's a -5 reward. Okay, so this is state space. Okay, and we only have reward assigned at terminal points in state space here. So now what we assume here is that there are actions. So when you're in state 1 here, Borchka can go down or to the right here, or south or east. And then we'll arrive in this state. So there's only a certain number of actions that are available in each state, and those actions carry you to the other state. Now, in this case, this is a deterministic model. So when Borchka is in this state here and goes to the east, Borchka will wind up in that state. A lot of times what you'll have in like robotics examples, for instance, is that when you do an action, sometimes it doesn't take you to the state you want to go into. So there's a distribution, a probability distribution of the transition. In this case here, we have deterministic transition, to keep it simple. Okay, so what do we have here? So we have these deterministic actions. Okay, and that's up, left, right, or down. And then we have what's called the value of a state. So if you think about the value of a state, it's like if you were like being completely rational, what would you price it at? What would you price that state at? So basically, value state number 6 here, that's got a value of 1. But let's look at state number 3 here. State number 3 has a value of 0, or the reward of 0, right? It has a reward of 0. But if you go south or down from that state, you'll get a reward of 1. However, what we're doing here is we have a discounting factor. We're discounting the future. We're discounting future rewards. And this makes a lot of sense if you think about something like money the question is like, would you rather have $10 today or $10 tomorrow? Does it make a difference? Yes, it makes a difference. It's better to have it today because you could actually earn interest on it. So the same is with you always want to kind of you're going to have a discounting factor for future rewards. So in this case, what that means then is it means that the value that we back up onto state 3 is a value of 0.9. It's not quite 1 because we have to. It's the 1 is 1 off in the future, so we have that discounting. And if you just continue here, we continue to back up these values. What we see here is we see that we get, for instance, the value of state 4. So the value of this state here is just 0.6561, because from here, the rational thing to do is to go up, right, and down, but that's pretty far off in the future that you're going to get your reward of 1. Okay, so this is how you, so every state has a value. Okay, so that's the idea of that, and the value is the future rewards you can get from that state. Now, what a policy does, so this pi, is that will give us the best action to take in each state. So this is actually what we're solving for in markup decision processes. We're solving for what's the proper thing to do at each state. What should I do now that I'm in this particular state? And I think at this point here, let's code is always it's always nice to look at some code. And this code here we're going to build on later when we talk about deep reinforcement learning. But in this example here, this is just classic. So if you notice here, it has in this case it's going to be a 6x6 world. We're going to use that doesn't matter. We're going to use a dictionary. Basically, we're gonna have it so that we basically can reach state space by using the x and the y as the key into this here. So this we're going to fill up the state space. These are the actions. Again, the actions that you can take at different states. The terminal, and then what is the value? So this will wind up being the value here that we're going to compute, and we'll just show this here. These are actually what happens when you perform actions. And here we do is we make the world. So we're going to basically go over the world here, and I'll breakpoint it so we can see it here. Okay, this is basically saying we take a random spot as the spot that there is the milk, and a random spot that there is the poison. So the cat should avoid the poison. Okay, here. Let's just breakpoint it there, and then we'll just do a debug here so we can look at this thing. Okay, there we are. Okay. Right. So this right here, what do we got here? Okay. The world. If I go up one, make world. Okay, so I've made the world, and if we look here, then what do we have here? We have the action. So these are 36. So basically at 0, 4, these are the actions that you can actually take. So sometimes when you're up against a wall, like this is an internal. 1, 3 is an internal, and you can take all 4 actions. So it restricts the number of actions you can take based on where you are in relation to a wall. So in the corner, this is a corner here, and you can only take the east and the east and the south actions. Okay, so this should all be pretty straightforward. The state space here is just a whole bunch of all right. Well, what do we have here? This is like the actual rewards that are in the state space. So the state space is actually the reward function. But notice here that it's got the cursive dimensionality, because if this thing was a 1,000 by 1,000 world, this would be a million values in the state space here. So the value hasn't been set yet, and we're going to actually figure out a way to discover the value through random walks, or to approximate the value through random walks. It's a very, very simple model. What do we have? We have the terminal states are right. So we have the okay. I think if we just basically say we're going to take 1,000 walks. So watch what happens here. So we're just going to walk through state space 1,000 times. We're not going to show it, what we'll do here is when you look at one of the walks, what it does basically, it just does kind of a random trajectory, trajectory through the space. And then if it happens to find a terminal, what it will do is then it will back that up through a certain portion of the trajectory. It will back that up doing discounting. Okay, so let's just, so you can kind of play with this code to see it. So if I, and at the end here, I'll normalize the value. So let's take a look at what the values wind up being here when we get to this point here. So now it's going to do, it's doing 10,000 random trajectories here. So it's going to take a little while. Now it's done. And then if we look at here, this is the value. Right, these are the values. So like this particular 0.53 has a value of 0.43. And yeah, so these are all normalized between 0 and 1. So right, so then let's see what happens with the walk. So look at the walk here. So in the beginning here, we have the cat at this position here. We have the poison here, and we have the milk here. And then what the cat does is it walks around here, walks to there, then it should walk up, and then it walks to the milk. So the policy that it's following, then it's basically using the value to calculate the policy. Okay, so this is just, so it's all in code, right? So if you want to kind of like, it's really simple. Okay, it's really simple. It's like very, very easy to kind of grok that code. Okay, so so that was that. So what's the problem with this? And again, the problem with the classic method, of course, is that it doesn't scale. I mean, like if we get, it's got the curse of dimensionality, right? Okay, so reinforcement learning is, MDPs go all the way back to the 1950s. Reinforcement learning has been mostly pioneered by, there's a huge group that's pioneered it, but the two people that get the most attention for it is Bartow and Sutton. And in fact, this Intro to Reinforcement Learning, I should just tell you that there's a 2018 version of this, which is, so if you're going to look at it, I'll update the slides and put that to 2018. You should look at the 2018 version of it. So it builds on MDPs, but then it assumes that the environment and the rewards are unknown. There's some different techniques that have been developed that allow you to do. This is still in the classic realm here. That this is where you're actually explicitly representing the states. There are some kind of classical approaches to that, but what we want to look at is we want to look at deep reinforcement learning. So if you remember about deep learning, what it can do is it can confront the curse of dimensionality. So, well, what do we do then? What are we going to do? And we're going to show this here in some code. What we're going to do is we're basically going to do the following. Instead of, what we're going to do is we're going to represent the state as two values, an x and a y coordinate. So what's your coordinate in the space? What's your coordinate into this world, right? And then what we're going to do is we're going to train a neural network. So we can do a whole bunch of random walks and get and start picking up examples of, we think the value at this spot here is such and such. Let's say that we think the value is minus 0.87 or something, or point something or other, because it was right next to the poison, and the random walk just immediately went to the poison, and then we generated from that a training example that says at this particular coordinate, it's got a bad value, right? The value, because we backed it up. So what we're going to do is we're going to build a training corpus by doing these random walks. We're going to have a whole bunch of things that say, at this X and at this Y in that little world, this is what we think the value is. This is what we think the value is. This is another, and we're going to have that as another example that we're going to go in. We're going to feed that through a supervised learning, which basically, it's not even supervised learning, it's a regression. We're going to try to basically learn what is the value at that particular point. And then this is a really simple case. All we're going to do then is we're going to use that value then to drive the decision making. So what we've done is, so we only have, now we might have a pretty wide, we're going to have a fairly wide, we'll play around with it, we're going to have a fairly wide hidden layer, but we've basically just taken, we don't have to explicitly represent all the states of the model. And what that does is it kind of smooths things out so that even if we have 1,000 by 1,000, the cat got something from the model that, okay, it's in this particular XY position that we never even had a random walk go over. But still, since the X and Y are close to somewhere else where we picked up some data, we know roughly what the value in that neighborhood is, okay? And so then we can use that value, and then it'll be able to guide its way to the milk. Okay, so this is that's kind of like really in the simplest way. That's the key contribution of deep neural learning, is this kind of collapsing everything down just to the X and Y coordinate rather than explicitly representing the states. And we'll show a little bit of code that gets to that. Some more general things to say about it, though, is that this deep reinforcement learning, so using deep learning with reinforcement learning, what that does is that basically some of the notable applications of this, things that really became kind of examples of doing deep learning, deep reinforcement learning. I got some real wins here. Atari games. So all the Atari games, just from kind of in a rudimentary sense, kind of built up. AlphaGo is really interesting. So it became the best Go player in the world now is a computer, and that wasn't true up until 2013, 14 or so. Okay, so that's a real achievement. That's a real milestone, because Go is. I mean, it used to be way back, like in year 2000. I was actually better than. I mean, I could play Go better than a computer, but now I can't. So. And I wasn't particularly good at Go, but I was good enough to beat a computer, but not anymore. We'll see later. Then we're going to get into this human reinforcement learning from human feedback and reinforcement learning from verifiable rewards. That will become what's really important in this course. But this right here was just a way for us to kind of like foreshadow that a little bit, because there's lots of technical aspects of that if we kind of cover it in a simple way here, then we'll be able to get to. Okay, so let's nose down into this deep value example for the cat. Okay. All right, guys. Let's show this very quickly. This is the deep value example of that. Excuse me. Of the little cat's world. So here's how it works. Notice one thing here. Let's see if I breakpoint it. I just want to run it here with a 6x6, the same size. But the point is that it's not going to occupy 36 positions. It's going to be much more frugal than that. So the rewards are at the different corners here. I just kind of had that set up here for testing. The basic way it works is the following. What it does, the first thing it does is go all the way down to the bottom here. It makes a training corpus. So let's look at the training corpus. The training corpus is based on random walks. So if I just run this right here, we'll see that. Okay, so now if I go down into this right here, you'll see that what it does, it's basically going through and it's just running kind of random trajectories over the space. But it terminates once it hits a terminal. So that's either a -1 or +1. And then it singles out a window here. This is like, it bounds the size of the window. This is like the last part of the trajectory. It'll take that and then it will do the discounting of whatever reward. And the reward here is either positive or negative. And so what it'll do here, let's just kind of run it through here and you'll see kind of the result of it. So if we look over here, it should be generating a training set. Okay. See, it's got 10,000 within it, so it's kind of a bit. Oh, it already went through everything here. So here's the training. So basically what it's saying here, it's a lot of examples here. So like, for instance, at the position 0.86, the value it thinks should be about that. That's one, from one of the trajectories was able to get that value. And then if we just go, see right here, here's a negative reward. So it associates with the state here. This right here, 0.333. I mean, that's like, this is the X and Y. So these are between 0 and 1. This is the X and this is the y. So these are just two value. They're just two position components. There's two values for that are the position x and y, and then this is the value at that particular spot inside the world that it's training on. So this is a training example here, and then what it does after that is it will actually train it. So it'll go through and it will simply push this through this kind of two hidden layer model. That's what it's doing. So it's just basically training that up. So it's training up a neural net, and that becomes then this training the actual parameters for the model. So if we notice here, it just kind of climbed down the loss here. So it was converging. Okay, first fairly quickly got to that loss, but here notice, and then here's the problem. So what it does is now the cat is here, and the cat should be able to then basically test the value. What's the predicted value at these x, y positions around it for the next actions? And then if you notice, it said, oh, it's best to go up. So it went up, and likewise it went up again, and it went over to the left, then it went over here, and then it's gonna wind up on the milk. Okay, so it's able to kind of sniff its way to the milk based on that learned value model. Okay, so the point here, and we don't have that much time because I have to get this ready for lecture here. The point here is that this can also be increased out to something like, I don't know how big it can go, 100 by 100, and this should scale. So it's again, it's not going to take 10,000 cells. It's just going to create a small little model that takes the x and y position into that 100 by 100. Okay, so x equals 1 is the 100th position, and y equals 1 is the 100th position. So that would be the bottom right-hand corner would be what would be accessed if for x equals 1, y equals 1. And then 50 and 50 would be 0.5, 0.5. So, but it's going to collapse all that down just into the x, y coordinate, and it sniffs the value at that point from a model that it learned over random trajectories, and it's able to kind of just guide it along its way toward the goal. So this is quite powerful in the sense that it's this is a witness to overcoming this curse of dimensionality. Because if we ran this thing under the classic method, it would be terrible. I mean, it's 10,000. Not only that, we'd have to have so many trajectories that would cover every one of the space. There would be no smoothing in between. So I hope that this kind of gives you at least an inkling of what the potentials are here for this deep reinforcement learning. Okay.